Welcome to all of you. It's great to see so many of you for tonight's campus lecture. It will be on the theme of the age of AI, our human future, and it will be given by Professor Daniel Huttenlocher, who is here on occasion of his appointment as Doctor Honoris Causa at EPFL. As for me, my name is Victor Pennacino. I'm a student at EPFL studying robotics for my master's. And yeah, that's about it. But to give proper introductions to our guest tonight, I will have to ask our president, Martin Vetterli, to give a proper greeting.
Excellent. Good evening, everybody. It's a great pleasure, of course, to introduce my friend Daniel Huttenlocher. Daniel is a very famous computer scientist. He was born about 65 years ago, something like this, right? His parents actually spent time in Lausanne. We just discussed it. His father is a neurologist, and his mother a cognitive psychologist at University of Chicago, where I guess you grew up in Chicago. I did infer from this information. And you did your undergrad at University of Michigan and then moved on to the one and only MIT for your PhD with a very famous computer vision specialist, but also already at the intersection with visual systems and neuroscience. And after that, Dan took an unusual path, maybe. He went to industry, but not anywhere, but to the Xerox Palo Alto Research Centers. Those of you who are in computer science, you know that was the place that invented a lot of the gimmicks we use now, which have been popularized by many other companies, but Xerox, if I have that information correctly. And then he joined a startup. I think it was in Intelligence Market, sounds like it was in New York. And from there, he went to Cornell in computer science, but always was very involved at the interface with real innovation, meaning writing also patents, not only papers. And then he became the inaugural dean and vice provost of Cornell Tech, which is a branch of Cornell University. If you know Cornell, it's up in Ithaca, which is very nice place, about 3 weeks a year. And New York City is, I have a lot of colleagues at Cornell, right? But Cornell Tech is, of course, the branch of Cornell in New York City, the one and only New York, on an island. It's interesting because it's a project EPFL had also looked at some point, but the winning team was the team of Dan Huttenlocher, and he became the inaugural vice provost at Cornell Tech in New York. Being very successful at building institutions, Dan was recruited to head, he was inaugural head of the new Schwarzman College of Computing at MIT, his alma mater, and has been running this fantastic new college at MIT since 2019. Meanwhile, he has written with very famous people. It was mentioned he has written a broad audience book called The Age of AI and Our Human Future with the one and only Henry Kissinger, recently passed away, and the former CEO of Google, Eric Schmidt. I'm not going to ask who actually wrote the book, right, out of these three very famous people, but it's a very interesting treatise about the impact of AI. It was published in 2021 and has had, of course, a lot of impact. The short story about the book is that AI is as important as a transformation as the invention of the moving type printing press, which has completely transformed not just the way we publish, but the way we diffuse information and interact on, for example, on scientific issues. And I think that will be one of the points he's going to tell us about. Thank you very much, Dan, for taking the time and giving us a lecture here. Dan, welcome.
Thank you, Martin. Definitely too kind an introduction. But all right, so I do have to say 2 words about the book co-authorship since Martin brought it up. But this book would not have happened without the COVID pandemic. But one of the things about New York is it's this amazing cauldron of people from all walks of life, and I got connected with Eric Schmidt doing the Cornell Tech project, and then we both met Kissinger in various settings, and we all started talking about the broader issues around AI. Nothing would have come of it. This was about 2016 kind of time frame, 17. But I moved back up to MIT in 2019 to start the Schwarzman College of Computing, and COVID promptly hit 6 months later. And so, kind of sequestered in this apartment, and we ended up spending a bunch of time on Zoom writing a book together. But all three authors wrote significant pieces of the book. And I will show you things that were written by my co-authors that you would think I wrote. All right. So this is not a technical talk. And in fact, this is sort of a two-piece talk. The first piece is related to the book and the topic of the sort of advertisement about what is AI and our human future. But then I also thought I would say a little bit about what we're doing at MIT, because it's actually very connected to this sort of broader study of artificial intelligence. So we all use this term. What is it? Well, you could start with something like this, technology for making, decisions and predictions and recommendations and creating content. But there's all kinds of decision-making and prediction software that's been around for an awfully long time, mathematical modeling, weather prediction, etc. So I'd say today, what's AI is really something that's trained to perform a task, rather than requiring precise human instruction to perform that task. So one of the interesting things that's happened with AI is the precise human instruction is now about how to learn how to do the task, as opposed to how to do the task. We've sort of gone one level meta. But what's really interesting about this, and this is what drove really a lot of what we talked about in the book, is that this produces systems that have results that have three properties that we don't associate with technology prior to AI: imprecise, adaptive, and emergent. Those are things that feel like humans, right? Computers used to be so precise that it was sort of laughable, but now they're imprecise in ways that we tend to associate not with machines. So I want to just give a high-level view of machine learning. So for the people in the audience who are machine learning experts, I hope you'll find this amusing. And for Pete, this is just to sort of level set all of us. But most models today are these what are called deep neural networks that have billions of parameters. And they're learned by adjusting these weights, these parameters, in an adaptive way to improve some sort of performance measure. And that's the learning process. So there are certain forms of learning. What's referred to as supervised learning, I tend to think of as, with humans, it's sort of classroom learning. The teacher's the supervisor. And this, in the machine learning world, tends to be things like where the data has been labeled by humans or by experts. Then there's unsupervised learning. This is a very deliberate picture, because things like clustering, those kinds of unsupervised learning techniques, I think pretty much produce results that are about as chaotic as an unsupervised classroom. And then there's the magic of self-supervised learning. So to me, one of the really amazing things that's come out of the last, say, 5 to 8 years in machine learning, of course, there's all the deep learning work, but there's the amazing power of these self-supervised learning techniques. Large language autoencoders, more general masked autoencoders used in computer vision and elsewhere. And so you can really think about that as, the very studious students who kind of can do it on their own. So having trained one of these models, you now do inference. And again, these are sort of two separate stages. So you can use this for classification. And of course, I'm going to use a computer vision example because that's sort of my technical history. So you show an image to one of these big models, and it can generate a label. But another interesting thing about these models compared to conventional sort of earlier attempts at machine learning is you can do this the other way around and do generation. So you can give it the label and have it produce the output. And of course, this is the whole crazy generative AI tsunami that's kind of, overcome us. But very interesting sort of set of models that can kind of be run both ways. So I like to think about AI as a funhouse mirror, right? If you've ever been to a carnival and looked at these strange mirrors that distort the world, it's an altered view. And I think one of the things that, in thinking about AI and machine learning more generally, you tend to find people who think that's good or that's bad. But it's neither. It's not inherently good, it's not inherently bad. In fact, technologies historically, I just started with something about this, it's different from the history of technology in the first slide. But here, this is something that AI shares with current this current technology shares with the history, which is that things are good and bad. Any new technology is in some sense a two-edged sword. So this means we have to be attentive when using AI. We have to pay attention to how it's trained. But again, I think the people who want us to pay attention to how it's trained, you always hear about all the errors and bias and so forth that these models can produce, and that's true and important. But the answer is not to therefore not train or use these models. Because in fact, trained properly and used properly, you can actually get better and fairer decisions than humans alone, not just introducing errors and bias. So there have been studies in the last few years in areas like pretrial detention in the US judicial system, in healthcare decision-making, where appropriately structured uses of machine learning actually yield better outcomes. It's not just the training, it also depends how it's used. So, and this is a big theme of the talk, when you're using these things collaboratively, you get very different outcomes than when they're the presumed expert. But there are some very nice studies that have been done lately, including by some colleagues of mine at MIT, like Marzia Ghasemi, who've looked at collaborative decision-making in clinical settings, yielding better results than the doctor by themselves. So human identity. So this is a place where, I'm not a philosopher. Luckily, I studied some philosophy in college. I don't know if that just makes me dangerous. But when we think about how we understand the world, still today, the sort of still pretty pre-AI age, it's been the same for, half a millennium, in the sense of there's human reason and there's faith. And what AI brings is something that's neither of those. It's not human reason. I underlined that because, if you watch, people like Sam Altman lately with the latest releases of some of what OpenAI is doing, he sort of refers to this stuff as if it's human reason. It's not. It's a new kind of intellect, which is also extremely powerful, that gives us a third way of understanding the world. That's extremely profound change. And it raises very fundamental questions about our identity as people. We're used to being the only intelligent things around, at least on this planet, if you believe in extraterrestrial intelligence. And there are other living things that are intelligent, but the human level of intelligence is very different. So this makes us uneasy and also makes it very hard to think about risks versus things that are just making us uneasy. So one of the things I wanted to dig into a little bit further around uneasiness is that AI increasingly appears to be human, but it's not. First of all, as I just said, this is a different kind of intellect. It's not human intelligence. But secondly, what makes us human is much more than reason, much more than intellect. And AI doesn't have human values, intention, motivation, morality, judgment, all kinds of things that make us human. But it can simulate these things in ways that make it look like it does. Now, I've had a debate with a 20-something a relative of mine about maybe we're all living in a simulation, and so this is but anyway, I'm not going to go there. So it's very easy to get sort of trapped by this, thinking that it's more than it is. And while alignment of AI with human values is an extremely admirable goal, it's not enough. It's just making the simulation better. In fact, it probably makes it even more likely that we will treat AI as it's human, that we will anthropomorphize AI. And particularly these sort of chatbot-style interactions where, and we've all seen that leading to undue trust in the chatbots. So human agency, very fun, another one of these fundamental attributes of what it means to be human. AI is enlightening and enfranchising or misinforming and disempowering, and that's nothing new. So mechanization for at least 150 years, probably longer, has had exactly that kind of duality. An assembly line, working on an assembly line is relatively disempowering, unless you get a good paycheck at the end, but the work is disempowering. Whereas, power tools that you can use as an individual, huge empowerment. But with AI, it's probably more fundamental because it's about how we think about the world, how we understand the world. So here's an example. Driver navigation software. AI can be empowering for an individual driver or disempowering for a rideshare driver because the rideshare driver is expected to follow the route that they get from the AI that did the route planning, whereas the human, it's just another input. If you decide, I'm going to ignore this stupid thing, that's fine, but a lot of the time it actually knows more than you do, and you follow it. So here it's exactly the same technology, and it's just a matter of use. So one of the things that is really striking to me, and this is some things that sort of I wish we'd kind of thought more about at the time that we were working on the book. So if you go back to at least 1960, some work by J.C.R. Licklider, who I actually had the privilege of knowing when I was a graduate student. He was still around. I was not a graduate student in 1960. I'm not that old. Wrote a paper called Man-Computer Symbiosis, so a very 1960s-ish sounding title, but it was about this fact that humans and intelligent machines together should be able to achieve more than either one alone. But in fact, almost everything we've been doing in the last 75 years around machine intelligence has followed a different thing that we're trying to optimize. We've been trying to optimize replacing humans. Well, replicating humans, but replicate. Once you've replicated, why not replace? Instead of focusing on what can we do better by these two things together, the intelligent machine and the human. And this is the result of Turing's view of the sort of imitation game as a way of evaluating intelligent machines. So this focus on collaboration rather than substitutions, especially important in areas that are high impact, like some of the ones we mentioned before. All right, So up until now, I've been sort of talking about try to get everybody a level set. Just there's AI experts and hopefully non-AI experts in the room. And then talking about sort of what this means for individual humans. I want to switch gears a little bit now and talk about AI in society. So this is a place where the horror stories that you see in the press and online and everywhere else tend towards these either dystopian prognoses or utopian kinds of outcomes. And they make very catchy headlines, but reality is generally neither. And in fact, I had some opportunity in the last few years to spend some time with people who write those Hollywood AI kind of stories about AI taking over the universe. And I said, really? Like, why? Why is that what we're telling everybody about this? And they said, oh, yeah, just we need a good conflict. The people harming the AI is not an interesting story, so it's got to be the AI harming the people. So one of the things I've been spending quite a bit of time doing, along with some colleagues at MIT lately, is actually spending time with people who are thinking about how we characterize AI in popular writing, movies, etc., but also spending a lot of time with people who are doing policy making with respect to AI. It's the same kind of issue. We all have these sort of science fiction views of things that tend toward dystopia or utopia, but reality is not going to be either. So every new technology initially seems like magic. That's what makes it a new technology. This technology is different in some ways, as we've seen. But we need a much deeper and nuanced understanding in the case of AI because of the kinds of issues that it raises for the nature of what it means to be human. I mean, our whole society is based on humans interacting with each other. So if this is challenging what it means to be human, it's particularly important as we think about AI's impact on society that we're building understanding that combines the social and technological aspects. And that's not easy to do. And this is because outcomes in the real world, as opposed to in fiction, tend to result from lots and lots of small, distinct, or sometimes large, development, deployment, and policy decisions. And so what's really important is that we have some shared understanding that guides effective incentives, and that those effective incentives then drive the decisions that are being made by individual companies, individual governments, individual people. So in doing that, here's the sort of crux of a really hard issue. Developing a shared understanding and shared norms is slow compared to development of technology. Because you really have to change how people think about things. You have to develop frameworks. Look, I think most AI experts don't know how to talk about AI in this kind of way. So maybe one kind of analogy that's useful for thinking about this is what we've started to call, some of the people I've been collaborating with, the fork and the toaster problem. I would guess that every one of you in this room knows when you're sticking a fork in a toaster and that that's not a good thing. It's a very well understood norm across, pretty much every culture. But this is what early toasters looked like a century ago. Like, pretty easy to stick a fork in the thing and electrocute yourself. And so the early technology was primitive with respect to whether it was easy or hard to use it in an unintended manner. You weren't supposed to electrocute yourself, but there were very few protections against it. But if we're going to try to assess responsibility, if we're going to say, was the user responsible, was the vendor or producer of this thing responsible, we need those norms. And then we need the kinds of guardrails that help enforce those norms, right? So a modern-day toaster, for the most part, has something that encloses those elements that have current running through them. So we develop norms, best practice guardrails, and then from that, you can derive well-understood legal responsibilities. One of the things about the rapid development of AI is, how are we going to do this? So there's been a tendency for people to try to jump across several stages of this and kind of, let's put some rules in place before we understand anything. And then there's been the opposite camp that says, well, these rules are stupid, therefore all rules are stupid, therefore this stuff should be ungoverned. And those are both relatively illogical arguments. So this is the problem I think we face, the fork in the toaster. Now, one thing, there's a promising sort of thing here. So when you look at the tech industry, they don't tend to view responsibility for software flaws as something that's the fault of the industry, right? You get these long end-user license agreements that nobody reads that you have to click on in order to. But something very interesting happened when ChatGPT and the other first generative AI tools started getting released broadly, which is that big companies refused to use them. And those are the people who are going to pay for them. Because they said, this is going to generate text. If my people have to go and fact check all of this text to make sure it's not infringing on somebody's copyright, why don't I just have them do it in the first place? So all of the big generative AI providers are providing some form of indemnification for copyright infringement to their paying customers, right? If you're using the free version, it's on you. This is a sea change from the tech industry, right? They're taking responsibility for some outcome, financial responsibility. So maybe what's starting to happen with machine learning and AI is so different from previous computing technology that companies that are producing it are going to take a different approach. I don't know. Maybe this is an aberration. Maybe it's a change. But it's a pretty striking thing. So anyway, fork in the toaster. All right, so AI systems are going to be, are going to continue to be very hard to oversee properly. So everyone talks about this black box nature of these systems and that we should improve the explainability, which I couldn't even bring myself to put here because I don't even think it's the right word, so maybe the interpretability. How do we really understand what they're doing? Maybe it's inherently limited. You can't get inside my head and figure out why it is that I said or did something. You can try to figure it out based on other things that I've done, based on statements that I've made, and so forth. But we don't expect human intelligence and behavior to be transparent. They're not. Well, go back to the beginning of the talk, where we're talking about how this machine learning was producing outputs that look a lot more like human-generated than like machine-generated. It may be inherent in those things that they're completely different from technologies that we know in terms of the degree to which we can really explain what happened. Right? It's not like the, national transportation safety authorities after an airplane crash being able to go and do a year-long investigation and say, this bolt failed. They have to, it's like doing neurosurgery to try to figure out why somebody did something, or fMRI or whatever. So safety of these applications is not the same as conventional technologies. And sometimes that's even an issue for the developers, right? So it's not even just for those outside of a team or a company that's building something, because what we're doing is developing this kind of software is we're developing the methods by which the thing learns. We don't really know what it learns. We know what we hope to get out of those methods, and we can run some tests to see if it's consistent. So next time somebody tells you they want to have explainable AI, I'd suggest thinking about it a little more. All right. So maybe now to some positive sides on society. So people learning from AI. This is, I think for me, the sort of big wow here was actually AlphaZero, the chess, learning how to play chess. There'd been computer chess programs for decades. They all beat people, but they did it in this sort of mechanistic, boring way that nobody who was an expert in chess found it all interesting. But because AlphaZero learned from self-play rather than looking at previous human gameplay, it actually evolved some very, very different strategies and tactics than human players. And some of those new approaches that it utilized have changed the way humans play chess. So grandmaster chess players now play chess very differently than they did before that. Think about that kind of powerful learning, discovering something that then changes how humans think about that thing, and applying that in areas like scientific or engineering discovery. I think that's really where we're standing right now. I would say I haven't yet seen anything that I find as powerful in the discovery realm as this was in the chess realm, and games are simpler than real systems, but there's been some pretty amazing stuff there as well, which I'll talk about in a second. I think it's also very important to remember that simulation and sort of direct learning from nature are very important parts of machine learning. It's not all about data, about people, right? Like you look at how, again, the sort of great generative AI race vacuum up all of the data about humans and human-produced things that you can. These latter two categories are at least as interesting. So I think we're going to have real revolution in the next decade of understanding new things and understanding things that we already understand in new ways, right? We already knew how to play chess. We already knew a lot about chess. But now experts in chess understand the game differently. Big caveat for teaching. I'm not a big believer in how quickly generative AI is going to revolutionize teaching. There's this long history of educational technologies that were going to change teaching that have all kind of crashed into the shoals of actual teaching. Be great if it does, but I'm going to bet on some really interesting scientific discoveries before we change teaching. So, on the scientific discovery front, science in many fields has advanced, and I mean, the scientific parts of engineering as well when I say science. So scientific discovery has advanced in many fields to the point where the systems that we're trying to work on and study and understand are of a scale and of a complexity that's very hard for people to grasp. This exactly is the kind of domain where the sort of Licklider view of humans and machines working together collaboratively offers huge opportunity. So I think that in areas like material science, I've seen some very interesting work in the last couple of years on graph neural networks, which are more structured than just the sort of vanilla deep network. And so you can use that structure to capture things like, there are symmetries in the arrangement of molecules and materials. And those kinds of inviolable laws, rather than sort of learning them from data or simulation, you can actually start to build some of those things into the structure. And what this has been allowing people to do is capture molecular constraints at very, very, very different levels and very, very different scales. It's that kind of problem that humans have a hard time with when you're working simultaneously on something that's at scales that are many decimal orders of magnitude apart from each other. So in chemistry and chemical engineering, I think there's been quite a bit of interesting work lately. So there's been a lot of work on machine learning for chemical discovery. The sort of dirty little secret of that is that a lot of those molecular structures any chemist would look at and sort of laugh. Yes, fine, that does seem to have the properties that you designed for, but nobody would try to actually synthesize that in practice. And in the end, you care about synthesis. If you're going to use the chemical compound for something, you have to be able to synthesize it. This is, again, one of these places where the complexity space just gets so huge when you're trying to think about this huge discovery space and synthesis simultaneously. So these are all things where scientists are working sort of hand in hand. It's not just set the algorithm loose. These are all sort of collaborations between scientists and the machine learning algorithms that they're running on things. And then, I think we have huge pressing challenges in climate and the environment. I wouldn't say I've seen outcomes here yet like I have in, say, materials science or the chemical sciences, but there's lots of interesting stuff going on now that I'm aware of in biodiversity and energy systems and in sort of how can we make sense of the planet at a scale. We have lots and lots of sensors around the planet, but again, integrating them at these scales is very hard to get anything meaningful out of. All right, so then I just wanted to, one more scientific thing that I wanted to do in a little more depth was protein folding, because this is really striking. So in 2021 already, so 3 years ago, I think it was the end of the calendar year, so just about 3 years ago, Science magazine named as the breakthrough of the year the use of AlphaFold and some other techniques that were developed around the same time, like Rosetta Fold, to predict the structure of any protein from amino acid sequence data. But this has been transforming the life sciences in a way that I think even when they named it this breakthrough of the year, they didn't really anticipate. I mean, every biologist I talked to. But we're now at a point where generative AI stands to have at least as big an impact. Because when you want to look at functional and regulatory issues, which are at least as important in the way proteins operate in a system's context, as well as structure, the structure alone is, coming from things like cryography and crystallography, or sort of freezing something literally in the cryography example. And in the functional and understanding regulatory things, these proteins are not completely rigid. There's another really interesting area of metagenomics, which is really sort of like, the protein stew and how do you understand things. And just one little kind of detail, but I think it's interesting and important illustration of the differences between these genomic language models and something like AlphaFold. So for these structure prediction algorithms like AlphaFold, which are phenomenally powerful, extremely useful, you have to have done multi-sequence alignment on, so you don't need structure. You're just working from amino acid sequences, but you have to have done multi-sequence alignment for these to work. So these have to be proteins that, you can align with known proteins and so forth. And then it's that sort of bundle of aligned proteins that you actually do this on. Whereas in the metagenomics arena, you just got like a stew of amino acids. You don't know what's going on here, of sequences of very, very, very varying lengths. And these genomic language models allow you to recover things even in these contexts where you don't know anything about the alignment of the amino acid sequences with one another. All right. So I said at the beginning I'm going to do two things. So part one was about trying to think about AI in broader ways than certainly I ever did as a technology person up until a few years ago when I started collaborating with Kissinger and Schmidt on what turned into the book. But a lot of these issues are driving what we're doing at MIT. So I got my PhD at MIT many, many, many decades ago, 35 years ago now. No, more than that, it was 35 when I got to MIT, 40 years ago. So why did I go back? Going backwards, never a good thing. Well, MIT made a commitment to really try to address this massive growth in computing and the rapid, rapid pace of change, and the fact that AI already was very different in, say, 2018 than it had been for decades before, and now we know how much more different it is in 2024. So there's huge student and employer demand, and one critical thing is it's beyond programming. It's about formulating and solving problems. So, when I grew up, nobody knew what a computer scientist was. Nobody knew what computer vision was. I always had to explain all of these things. Now everybody thinks they know what a computer scientist is, and they think it's a programmer. So I'm not sure which is worse, but the forward-leaning companies that I know of know that they're not hiring programmers with most computer scientists. It's extremely important, hopefully, if you weren't convinced of this before, that the social, ethical, and policy aspects are something we study in conjunction with the technical ones. Research in almost every discipline is being transformed by algorithms and AI. But computing itself is changing really fast. Like, we just launched last year a new artificial intelligence and decision-making undergraduate major at MIT within the EECS department, along with our EE and CS majors. But like computational science and engineering, operations research, and statistics all used to be more different from each other than that. Machine learning is just changing all of these fields. We don't know what the boundaries are anymore. So the College of Computing was to address that era, that new emerging era. And if you're going to make any kind of change in any organization without any new resources, it's close to impossible. In academia, it's really impossible, because every faculty slot is like, everyone knows that they own it, even if they don't actually own it. So every faculty slot has multiple owners in terms of departments or deans or whatever. So 50 new faculty slots. MIT's not big. We have about 1,000 faculties. That's 5% growth in the faculty. Half of those were called core faculty, and they're in electrical engineering and computer science. So that's EECS and the new AIND. And half are what we called shared positions. They're based in departments outside of computing to do work that infuses computing in a discipline. So in the 5 years I've been at MIT, we've hired 48 new faculty. We've used 2/3 of these 50 faculty slots. So the other 15 have been hiring that we would have done anyway in that time period. But it means 2/3 of the hiring in that time period has been the expansion. But the thing that I find most exciting about this is that half of those 48 faculty we've hired are doing this infusion of computing in other disciplines. And it's a mix of core and shared. So EECS itself is also broadening. Core computing is broadening, as well as these other departments. So these are the areas that we've mainly been focused on: algorithms and society, including faculty in political science, philosophy, economics, the management school, computing and human experience, more connected to the humanities, arts, and social sciences, scientific discovery, which I just talked about. Computing and climate has a bunch of scientific discovery in it, but very focused on certain things. Health and life sciences, computational fabrication, and quantum. This is not all the hires. This is the ones who are working at this boundary between computing and some other discipline. There's a whole other set. And about 2/3 of those are working in AI, the ones working at the boundaries. Not surprising. So I'll just pick two quickly. Connor Coley's in chemical engineering. He's been really leading the work going on some of these problems that I mentioned around chemical discovery and synthesis. And Priya Danti is in electrical engineering. She works on power grids, but on very novel machine learning approaches that use sort of global scale data observation to better control power grids. So education, super important. Very much a core focus of the college. It's not just about hiring faculty. So we developed something called the Common Ground for Computing Education, whose mission is to develop broadly applicable computing subjects that bring together multiple disciplines. Very few disciplines teach computing in a way that's applicable outside of their discipline. Right? Like if you're a material scientist and you learn about computing, it's probably numerical methods, things that are very closely tied to the kinds of numerical simulations and optimization that you do in your field. That makes sense, you're a material scientist. But as fields are starting to have the forefront of machine learning matter more and more, the idea is to start to build expertise in our students and in our faculty to teach our students to have computing that's more broadly applicable. And this is actually enabling new degrees also. So this is an eye chart. It's not to read it. It's for me to look at two things. So these subjects, I mean, MIT, everything's numbered, nothing, you know, so those of you who know the institute at all, so in the eye chart there you can see, but so we had to get subject numbers that worked across all of the MIT courses, so we invented a new namespace. So there's a class 6C01, which is modeling with machine learning, course 6 is ECS. But then there are 7 other departments that teach a module that plugs into that takes these modeling techniques and applies them in their department. And one of the things we've been able to get is some of these departments decided, you know, we don't all need a module. We'll co-develop a module. Now we're getting this step towards having broader computing, not just by bridging to ECS. This is on the other end of the spectrum, interactive data visualization and society. This is somebody in comparative media studies and writing, somebody in urban studies and planning, and somebody in human-computer interaction and computer science, teaching a really amazing visualization class. These are, you know, by MIT scale, pretty good-sized classes, kind of about 150 to 200 students each. All right, so now the next thing in the college I wanted to just touch on here briefly is the social and ethical responsibilities of computing, and I'm just going to illustrate a few things we're doing. We started this Envisioning the Future of Computing prize 2 years ago. I've just been blown away by that. I mean, like, you know, it's always fun being around really smart undergraduates and graduate students, but just these are students who wrote things that weren't necessarily that tied to what they're doing in their kind of, you know, day job of getting a degree. That were just very creative ways of thinking about computing and the simultaneously considering the positive and negative aspects of advances. We have a scholars program that has scholars from across all of MIT working on computing things. I mentioned that some of what we've been doing is trying to engage with policymakers. We've been spending a bunch of time in DC, since that's the local policy nexus for us. In the US, and a brand new class that's being done between the social and ethical responsibilities of computing and the common ground. It's a philosophy faculty member and a computer science faculty member. I'm very hopeful, actually, we'll hire somebody in history this year who could become part of this as well, on ethics of computing, because the historical lens on ethical questions is super, super important. So, that's what I had to say in my prepared remarks. I think building an AI future is up to us, all of us. Whether you're a computer scientist, an engineer, a philosopher, a political scientist, just somebody interested in this stuff from, you know, completely outside of a place like EPFL or MIT. I think a very important part of this is how do we foreground more these machines as collaborators and partners? How do we facilitate the kinds of new insights, discoveries, and innovations on the toughest problems? And how do we make ourselves be attentive? It's not something we're not good at. Maybe AI can help us with. Simultaneously being attentive to positive and negative aspects of things. We tend to veer towards, oh, it's just, you know, terrible, it's going to kill us all, or it's amazing, it's going to save the world. But we really have to maintain both of these together. So with that, thank you very much.
Well, I would like to first of all thank you, Professor Huttenlocher, for this very insightful talk. We'll now have a 10 to 15-minute Q&A where you'll have the opportunity to ask your most burning questions to the professor. On each side of the room, you can see there's actually a mic, so over there and right here, where I'm inviting you to come down and start queuing up if you have a question. And then when I will design you, you can please ask away, speak loudly and clearly inside of the mic. Now, so that most of you have the time to come down from your places, I'll first start with a question of my own. So, you actually talked quite a bit at the end about the work that you're doing at the Schwarzman College of Computing, namely what you're doing with policymakers back in DC. Now, I wanted to talk about recent efforts in regulating AI. Given the breadth and scope of the technologies that fall under this umbrella term and its ever-increasing speed of development, as one set of laws might be voted, industry and academics might already have rendered it obsolete by considering new applications. My question is, I have two. Do you believe in the power and capability of regulating bodies to face the latest ethical and societal challenges they raise? And what is the role and shared responsibility of an engineer or a company or an academic threading on these new waters when it comes to answering these challenges when they're unregulated or poorly regulated?
Yeah, no, it's a great, very important question. I think to answer your question, I have to first say something about what I think is the right approach to be taking generally. I think that horizontal regulation, that is AI across every discipline with a single regulation, is very risky because it's likely to actually simultaneously over and under regulate AI depending on the domain. So domain-specific AI regulation, I think, is the place to start and start developing better understanding. And let me just give you an example. Like, we regulate doctors, we regulate lawyers, we regulate all kinds of things that human beings do. We need to make sure that we're applying those same kinds of standards to the use of AI as we do to humans. Otherwise, we create this very strange set of incentives and things. So, having done that, if that's an approach that one follows, then I think that helps. It says, what kinds of experts do we need to bring to bear? We need to bring AI experts, healthcare experts, if we're talking about the health arena, and people and regulatory experts together. And it's really all three of those. So I think if we just take AI and regulatory experts, we're going to end up with something that can make us very unhappy. And then I think, in that mix, academics play an important role, but maybe less important than we think.
Thank you very much. Please, so over there, you're the first one to rush to the mic.
All right. Thank you very much.
It's very unbalanced.
We'll try to make it work.
Ed Bugno from Computer Science. First of all, it's an honor to have you here tonight, and thank you.
Oh, it's my honor to be here.
And thank you for putting EPFL and MIT in the same sentence. My question is basically on sort of your view on the gap between our ability as scientists to understand how and why AI works the way it works, and the deployment of these technologies by the tech platforms who quite frankly don't really care that much to really understand whether it works or the limitations of the failure mode. Now, that gap has existed since the beginning of at least the digital transformation and the growth of the internet 25, 30 years ago. And it seems to be growing, right? In the sense that every 6 months, every year, there is a breakthrough that we have a hard time as scientists understanding. And I guess, first of all, I'm interested to see whether you share the view and what can we actually do about it, or is it something that we should be particularly concerned about? Thank you.
So I'll go back to the fact that I'm going to go back to the fork in a toaster. I think that even the pre-AI boom digital world, as you pointed out, was changing very quickly. Changing quickly enough that we didn't actually understand the fork in the toaster for many of these things. Coupled with a very innovation-oriented environment, which I actually think is good. I'm a firm believer in innovation, but it meant that there was a lot of things happening quickly. Still are. But there, I think we're starting to get some insights, right? So I'm going to speak from the US legal framework kind of point of view because it's what I understand the best. If you look at the that's what's usually referred to as Section 230, right? That's sort of regulating the, sort of saying that digital service providers can't be held responsible for the content that others put on their network. I think we're starting to see an understanding that, yes, that's fine if you, as the provider, are not boosting that. But if you're taking that and you're saying, this one's really important, I'm going to shove it down everybody's throat, and this other stuff I'm going to bury, that's an editorial type of function that there should be some responsibility for. And we're starting to see cases in various parts of the court system in the US that are starting to push at those assumptions. But it gives you a sense of how long that takes. Section 230 is from the dot-com boom in the late 90s, right? So, and I think it was important for a lot of the early innovation. So I think one of the things is to try to think about how can we accelerate some of that understanding. I think some people feel like it's about time, but a lot of them were saying wholesale repeal of that protection, which probably was going too far. So it just takes time to get this kind of understanding. So now with widespread use of machine learning, these are fundamentally different. We don't understand them in a fundamentally different way that we don't understand conventional. In the end, if some conventional piece of software is doing something, some very painstaking piece of work, it is like finding the broken bolt in the airplane. Can't do that with machine learning models. So I think one thing that we all should be doing, when I'm just going to say we all technical machine learning people, is just much better ways to start to characterize what's going on in these models. And people are starting to do that, but that's a place where I think the research can't move fast enough. And for the most part, the private sector, not really, like if they thought they could, train a 10 times more powerful model with, half the compute power they're using today, then they'd start to work on those problems because they're running into things like, not enough power in the power grid. But purely for the understanding side, I think that's something we should really be working on. It's a very good question.
Thank you very much for the question. I think now we can go to you, sir, on the left.
Hi, Professor. So I think at the end of the previous question you mentioned, there is some kind of ongoing researches on characterizing the models. This is what I believe something that we are not mature.
Oh yeah, people are definitely working on those problems. I'm just calling for more.
so in this case, do you think that will the mathematical researchers play a more important role in the evolution of AI in the future? And as you have discussed in the PowerPoint, we haven't seen lots of mathematical researchers in this introduction. So I am curious about how much of this we'll do in the future. Will it become more important, or does it mean that it's there and it's already being developed, and elaborating on that, will such researches become more important, or will it have a bigger market in the industries?
Yeah, no, great question. So I, as a computer vision researcher for many, many decades, every computer scientist in here should be taking more math than they are, just straight out. There's just not enough. In fact, one of the things we did when we revamped the CS curriculum at MIT is we're requiring things like linear algebra that we weren't requiring in computer science. There's a lot that I'll say that applied mathematicians, and I'll throw physicists in that category. That is, not every experimental physicist might view that as a compliment, but I'm intending it as a compliment. have done historically in this area and can and will continue to do. There are, so I think that, you know, the pure math side I don't quite understand, at least in my limited understanding of pure mathematics, the connections, but in applied math I think there's a lot to be done and there should be more. But every CS person should take more math than their curriculum requires.
And so what will this trend, also...
I'm sorry, we're going to take a question from someone else because we don't have much time, there's a bit of a rush. But thank you very much for your question.
Oh,
Thank you.
We're going to take a question from you on the right, sir, please.
Thank you. Andre Villarreal. I'm alumni of EPFL and MIT. I originally come from Bolivia and recently was given a talk on the developments on AI since the times I was a student too, 30 years ago almost. And interestingly, the worries that people have over there are very broad, as in they're not part of this world we're discussing here, certainly not the part of the world where AI is being built, where the science is advancing, or where the patents are being held like China. I wonder what in all that you mentioned, the ecosystem you're building at MIT or around MIT can help countries that are trying to make sense of their situation in this developing, you know, development of humanity.
Yeah, it's a good question and a hard problem. I think one of the things that so there are several faculty at MIT, more in Sloan School, in the management school, who have been working with sort of how to help, you know, countries all around the globe come to grips with understanding the AI revolution better and what it might mean in their economy and in their country. But I haven't been that close to that stuff lately. I spent some time with those people when I first got to MIT, but it's now back to MIT, but it's now 5 years ago. But it's a super important problem. There's a guy, Luis Vitageri Caso, who he was the foreign minister of Mexico like 2 administrations ago. So I mean, he's been in the trenches of trying to get policy stuff done and doing things at a global scale. So he's been helping lead that.
Thank you.
Right. Thank you very much, Professor. We're going to have one last question. Unfortunately, it's a bit of a time rush. To you on the left, please, but please keep it short.
Hello. A lot of names in the tech industry, and specifically in AI, are betting on scaling models to achieve superintelligence, and that obviously requires a lot of venture capital and energy. I would love to know your opinion about this. Can we buy our way into superintelligence, or does that require a secret recipe?
Very good question. You can probably guess my answer, but exponential growth goes like this. Well, this if you're lucky, that if you're not lucky. So, you know, hard to tell where we are on the growth versus the asymptote versus potential decline. But I think there are indicators that are pointing to the fact that the asymptote's not that far away. So when you have the people building these leading models talking about, you know, $100 billion clusters for training models, like the biggest fabs in the world cost maybe 30 billion, right? So we're now, it's more expensive than the most expensive industrial things that we build in the world. The power for that is also not quite there. Let's build new, you know, micronuclear reactors that really are, you know, all my friends in nuclear science and engineering say won't be ready for another decade. So I think we're starting, the asymptote's going to be there in terms of just raw growth. But necessity is the mother of invention. I actually think that's good. It means returning to the kinds of fundamental questions that academics usually look at of, you know, more efficient algorithms, better ways of structuring problems, you know, the things that have driven exponential curves to keep growing has not been simple scaling in technology, it's been invention. And so I think we will see a lot of invention there. I guess I view superintelligence as a thing from science fiction. I have not drunk the Silicon Valley Kool-Aid, so that's... Many friends of mine have, but I have not. So, yeah, I think there were two parts to your question, the scaling and then superintelligence. So, thank you.
Beautiful. Thank you so much to all of you who have burning questions. Unfortunately, we won't be able to answer them right now. But as we close off this session, thank you again, Professor Huttenlocher. Unfortunately, the professor and Martin Vetterli will not be able to stay for much longer as they have to rush due to prior commitments and will therefore not be able to attend the following aperitivo. But before you go, Professor, I'd like to know, do you have one closing remark, perhaps a piece of advice for the students in this room here who will help shape the world of AI tomorrow?
Well, I already gave one, learn more math. Another one, which is harder, because you really have to start to figure out how to engage with people in the social sciences, in the humanities. These broader questions are not things that as technologists we should say, oh, the social scientists should work on that, or oh, the humanists should work on that. We need to be working together on it. So that's the task I would have for you. Okay. Go take an ethics class. Meet some of the people there. I mean a real one. Oh gosh, I shouldn't say these things out loud. So the word ethics, right? In academia, we have all these specialized definitions, right? So ethics is a subfield of philosophy in academia. In the world, ethics, which I've been trying to call ethical behavior, that's a general phrase. When I said take a class in ethics, I meant the subfield of philosophy. It will blow your mind.
Okay. Thank you very much, Professor. You're well deserving of your EPFL doctorate. Congratulations. Thank you.